In this video, we'll be talking about 2.5 Lewis diagrams. The topic is to represent a molecule with a Lewis diagram. This is our intro video to Lewis diagrams. Some of these diagrams can be quite complicated, and there will be more videos. This is just the first one. So the skill is representing data and phenomena. The key point is that Lewis diagrams can be constructed according to an established set of principles. A Lewis diagram is a representation of a chemical substance. It shows the connections between atoms. It displays the bond order, single, double, triple, that are between atoms, and shows the valence electrons that are not used for bonding. So here we have an image of acetone, and you can see that each carbon atom is bonded. This is a single bond to a hydrogen. In a single bond, that represents 2 electrons. So each of these bonds is 2 electrons, and then we have a carbon double bonded to an oxygen. So each bond represents a pair of electrons. So this is 4 electrons in between the carbon and the oxygen. And then these 2 dots on either side of the oxygen represent non-bonding valence electrons. And notice that each carbon atom is touching a total of 8 electrons. So this carbon atom has 4 bonds. Each bond has 2 electrons. So there is a total of 8 electrons surrounding that carbon atom. And this is the purpose of bonding. 8 valence electrons is a full outer shell, and that means that the atom is stable. And so carbon needs to be touching 8 electrons. Hydrogen is in the first shell, and in the first shell there can only be, hydrogen only has 1 shell, and in the first shell there can only be a total of 2 electrons. So therefore hydrogen can only form 1 bond because this bond represents 2 electrons. So each hydrogen atom is touching 2 electrons. Oxygen also needs a total of 8 electrons to be stable, and so it has 2 bonds. Each of these has 2 electrons. That's 4 electrons, and then 5, 6, 7, 8 with the lone pairs. This carbon atom also has 4 bonds, so a total of 8 electrons are touching it. So again, these letters are the chemical symbols of the atom. The dashes are used to represent bonds and are the same as 2 electrons, and occasionally you'll see dots as well. I prefer to draw it with the lines, with the dash, because I think that is more clear. And then the dots are used to represent the valence electrons that aren't bonding. So Lewis dot diagrams can also represent an individual atom. The Lewis dot diagrams only represent the valence electrons in a given atom. So hydrogen is 1s1, it has 1 electron in its first energy level, so it has 1 valence electron as well, so it just has 1 dot. Helium is 1s2, it has 2 electrons in that first shell, but it only has 1 shell, so that's the valence shell, so it has a total of 2 electrons. Lithium is 1s2, 2s1, so the second shell is its valence shell, and it has 1 electron in that second shell, so therefore it has 1 dot. Nitrogen is 1s2, 2s2, 2p3, so notice in the second shell it's 2s2 and 2p3, so it has a total of 5 valence electrons, which are represented by these 5 dots. Notice that not all of the electrons are clumped together. The electrons are generally spread out. You put 1 on each side before pairing them up. And this is because this shows that these 3 lone electrons want to bond with other electrons. And so nitrogen tends to form 3 bonds. Fluorine has 7 valence electrons, 2s2, 2p5, that's total of 7. So it just has 1 lone electron, and so it forms only 1 bond. Neon has 8 valence electrons, and therefore it does not form any bonds. It has no lone electrons. You can see from the periodic table that this pattern exists, where each element in each group has the same number of valence electrons. So in group 1, we just have 1 valence electron. Group 2, we have 2 valence electrons. Group 3, 3, or group 13, you can also call this group 3A, has 3. Group 14 or group 4A has 4, and so on. The exception is that helium in group 8A only has 2 electrons, and that's because it has a full shell, just like all of the other noble gases, but it only has the first shell, which can only have a total of 2 electrons, that 1s shell. So you can see that boron has 3 electrons, so wants to form 3 pairs. Most elements want to have a total of 8 electrons, 8 valence electrons, but boron is an exception. It will occasionally have 8 valence electrons, but it can also just be touching 6. So it would just touch 3 bonds. Each of these bonds have 2 electrons, so that's a total of 6. Carbon wants to form 4 bonds, so you can see it becomes CH4. Nitrogen has 3 lone electrons, so it will be NH3 and form 3 bonds with nitrogen. And then notice nitrogen would have 2, 4, 6, 7, 8 electrons surrounding it. And so oxygen would generally form 2 bonds, that's H2O, and fluorine would form 1 bond with the hydrogen, and neon doesn't tend to bond. How to draw a Lewis diagram. I would recommend pausing the video and jotting down these notes. This is going to help you draw any Lewis diagram. So the first thing you need to do is determine the total number of valence electrons. The second thing is write a skeletal structure with the least electronegative atom in the middle, usually, and then connecting the other atoms with single bonds. Third thing is to subtract the electrons used for bonding from the total count. And remember that each bond is 2 electrons. Then add electrons around each peripheral atom until each one has 8 total electrons, or you run out of available valence electrons. This is called the octet rule, and although it's not always true, we saw hydrogen won't have 8, boron won't necessarily have 8, and there are atoms with expanded octets that we'll get to later. It's usually true, and it's a good rule of thumb to follow. If there aren't enough electrons, you need to create a double or a triple bond. And if there are too many electrons, add additional electrons to the central atom if it's in period 3 or below. And we'll talk more about that in a later video. So our first practice is oxygen. So the first thing we need to do is count our valence electrons. Well, we have 2 oxygens. Each oxygen has 6 valence electrons. So that's 6 times 2, which gives us a total of 12 valence electrons. There's no central atom because we only have 2 oxygens. So we're going to start by putting our 2 oxygens down and bonding it with a single bond. So now we've used 2 electrons. So we only have 10 electrons remaining. So now I'm going to try and make my oxygens have their full octet. So each oxygen has 2 electrons right now. So I'm going to go 3, 4, 5, 6, 7, 8. And just to make sure, I have 2, 3, 4, 5, 6, 7, 8. I have a total of 12 electrons. So I can draw 10 more dots, and I've drawn 2, 4, 6. So I have 4 more to go. So I'll draw these 4. So now in this image, I have a total of 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But each oxygen atom does not have a full octet. This one on the left has 8, so that's good, but the one on the right only has 6. So what needs to happen is this beautiful thing called sharing. So I'm going to remove these 2 electrons. And I am going to create a double bond. So these 2 electrons on here have moved so that they're shared between both oxygens. And now I have 1, 2, 3, 4, 5, 6, 7, 8, because each bond is 2 electrons. So I have 8 electrons around this oxygen, 8 electrons around the oxygen on the right. And I've used a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. So this is good to go. Another way to do this is to draw the Lewis dot structure of our oxygen, like it was in the previous slide. So we have 2 oxygens, and notice each oxygen has 2 electrons that are not bonding. So I can connect these 2 electrons, and I can connect these 2 electrons, and now I have a double bond as well. So you can see that the oxygens need to bond twice. So the next, just another note, how do we actually know that oxygen has a double bond? Well, like you've learned previously, a double bond has a higher bond energy than a single bond. So we know that oxygen is going to be doubly bonded because the bond energy of oxygen is 495 kilojoules per mole versus fluorine, which sits right next to it on the periodic table. It shouldn't be that different. They have the pretty similar radius, but fluorine has a bond energy of 155. So oxygen's bond energy is much, much higher, which supports the theory that, or the fact that oxygen has a double bond. Okay, our second practice is N2. Go ahead and pause the video and try and draw N2 on your own. Again, our first step is to count the valence electrons. Nitrogen has 5 valence electrons, so 5 times 2 gives us a total of 10 valence electrons. And then again, we just have 2 nitrogens, so I'm just going to bond them with a single bond. So I've used 2 electrons, so I have 8 more to go. Well, I know that this nitrogen on the left needs 6 electrons, the nitrogen on the right needs 6 more electrons because they already just have 2. So I know that I'm going to need a double bond at least. So now I've used 2 more electrons. So now I have a total of 6 electrons to go. But each of my nitrogens needs 4 electrons, so I'm going to need a triple bond, and then I can add the remaining electrons. So notice I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, and each nitrogen has 8 electrons touching it. And again, you can see that we have a triple bond nitrogen based on the bond energy. It's much greater than oxygen's double bond, which is much greater than fluorine's single bond. Go ahead and pause the video and try CF4. So for CF4, we have 4 valence electrons from the carbon plus 7 valence electrons from the fluorine, but we have 4 fluorines. So 7 times 4 is 28 plus 4 gives us 32 total electrons. Carbon is less electronegative than fluorine, so it'll go in the middle, and then I will bond each fluorine around it. And then I will, so this is 4 bonds, and each bond has 2 electrons, so 4 times 2 is 8, so 32 minus 8 gives me 24. And notice that the carbon has 8 electrons surrounding it, and each of the fluorine needs 6 more electrons to have a total of 8 electrons surrounding them. And so, 24 divided by 6 gives us 4. So we will have enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that's our structure. The last one is CO2. So again, pause the video and try this on your own. Carbon has 4 valence electrons. Oxygen has 6 valence electrons, and we have 2 of those. So 4 plus 12 will give us 16 total electrons. Carbon, again, is less electronegative than oxygen, so I will bond each oxygen to the carbon. In these bonds, I have 2 bonds, so I've used a total of 4 electrons. So I have 12 electrons remaining. Each oxygen needs 6 more electrons. And the carbon needs 4 more electrons. So I have 12. So I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But my carbon still needs 4 electrons. So we're going to do the beautiful act of sharing. So I'm going to remove these 2 electrons from oxygen, and I'm going to make both carbon and oxygen satisfied by adding a double bond. So now carbon has a total of 6, this oxygen has a total of 8, this oxygen has 8. So carbon needs 2 more, so I, again, am going to remove 2 electrons from oxygen and create another double bond. And so that'll be my structure. And we'll soon talk about why you wouldn't have 1 triple bond and 1 single bond.